In this video, we're going to look at something called a fundamental particle and what that is, and then how those fundamental particles are arranged in something called the Standard Model. Basically, it's the periodic table for particle physics. Well, to start us off, let's talk about this quest for the fundamental particle. We knew for a long time that things were made up of smaller things. We called those things atom. Atomos means uncuttable. Well, we then learned that there are things smaller than an atom. An atom is made out of electrons and protons and neutrons. And we thought for a long time that, okay, now this, a proton or a neutron or an electron, that is a fundamental particle. Well, then other particles started to become discovered, things like a muon or a boson. And these other particles didn't really fit any sort of pattern. So that led us to look a little bit deeper. Now, our current understanding of a fundamental particle are things that are inside of protons. We know that now inside a proton, we have something called a quark, up quarks or down quarks or strange quarks or charm quarks. And those quarks are part of these list of what we call the fundamental particles, the smallest building block of nature. And you need to know these fundamental particles. Well, you're going to be given some resources to help you figure out and understand these. You don't have to memorize all of them, but you do need to be able to read some important properties from a list of tables. First is a table of quarks. There are 6 different quarks. We have the up, down, charm, strange, top, and bottom, represented by the symbol shown here. The table that's given to you in the IB Physics data booklet is shown up here. You'll notice that up, charm, and top quarks all have a charge of 2/3, and down, strange, and bottom quarks all have a charge of -1/3. Now that's going to seem kind of random, like how could you possibly have an almost full charge, and how could you have a charge that's a -1/3? Well, these quarks will always combine in either 2s or 3s. And when they combine, you'll always get an integer number of charge, either a +1, 0, or -1 charge. Now, these quarks have a strangeness number to them as well, and that strangeness number is 0 unless you have a strange quark, then it has a strangeness number of -1. You'll also notice that these have something called a baryon number. We'll talk about baryons in a little bit, and that baryon number for all these quarks is 1/3. Now, there are 6 quarks that are shown here, but there's actually 12 quarks because all of these quarks have an anti-quark. These antiparticles have an opposite charge and their corresponding particle, and they have a bar over the symbol. So for example, you can have a strange quark, which is a -1/3, or an anti-strange quark, which is just an S with a bar on the top, which is a +1/3. So you have an anti-up, anti-charm, anti-top, anti-bottom, anti-strange, and anti-down. Now, you also have in our list of fundamental particles the leptons. These leptons are things like the electron or the anti-electron, which we call the positron. Now, there are other leptons as well. So, in the family of electron, we have the electron, the muon, and the tau. These all have a charge of -1. So you are familiar with an electron having a charge of -1. You can also have an anti all of these, which would have a charge of +1. That'd be the anti-electron. We also call this the positron, the anti-muon, and the anti-tau. Those would all have a +1 charge. We also have these chargeless, these neutral particles that are leptons called neutrinos. These are the electron neutrino, muon neutrino, and tau neutrino. You'll see that subscript represented each of those different types. You can have antineutrinos as well. You may remember an antineutrino showing up in beta negative decay. All of these leptons also have a number associated with them called a lepton number. The lepton number is 1 unless there's an anti-lepton, then it's -1. Now, that feels like a lot of different things and a lot of different things to keep track of. We will revisit this later on, talking about all these different nuances and these numbers that are associated with these particles. So I want to show you what it looks like in the data booklet. It's these exact tables. They just don't look as pretty as they did in the last slide. They show up here in subtopic 7.3. One thing that I do want to point out, something that has always bugged me in the data booklet, the charge on these down, strange, and bottom quarks. It has a negative in there. It's negative 1/3 electrons is the charge. But the negative, the way the font works out, it looks like it kind of goes in there. So it's easy to miss the negative if you're not looking for it. So just remember that is a plus 2/3 and a minus 1/3 for those quarks. All right, if you really wanted to go at it, you can list from these things in the table every single one of the 24 particles that we have listed with the 6 quarks and 6 leptons, as well as their anti-quark and anti-lepton pairs. And you'll see all of that kind of showing up in here with their charge and baryon number associated. All right, so that leads us to classifying particles. On one side of our fundamental particles, we have these leptons. These leptons are what we just organized in that table. The common leptons that we'll see is the electrons, the muons, tau, and then, of course, all the neutrinos associated with those. Of course, antileptons are also leptons that categorize in that category there. That means that there is nothing smaller than an electron. The electrons aren't made up of any other parts to them. On the other side of this tree of fundamental particles, or different particles that we have in nature, we have the hadrons. Hadrons, like the Large Hadron Collider, which you may know of, are anything that is made up of quarks. These quark-based particles can be categorized into two different sets. We have the mesons. These are things that are made out of two quarks. Mesons, some examples of them are the pion, the kaon, and some others. There are hundreds of them, so you won't have to memorize these. You'll just be given, this is a meson, or you'll notice that it's made out of two quarks. That means that it's a meson as well. The other side of the hadrons, kind of under this umbrella, is the baryons. Baryons are something that you are familiar with, whether or not you realize it, because baryons include the protons and the neutrons, as well as several others that are in that list. While mesons are made out of two quarks, baryons are made out of three quarks. But all of these are under the umbrella of hadrons, which are particles made out of quarks, either two or three. So leptons or hadrons can be mesons or baryons. Now let's look at baryons. Specifically, let's focus on the proton and the neutron because these are baryons that we use all the time. They're made up, they are in every atom that we have. And it is important for us to know how these baryons of protons and neutrons are comprised in their quarks. Well, the most common quarks are up quarks and down quarks. And this is what protons and neutrons are made out of. Now, if you look at your table here, you'll see that the up quark has a charge of 2/3 and the down quark has a charge of minus 1/3. Now, with that as our possible combination, our rule is that the charge will always end up being an integer that's -1, 0, or +1. We know that a proton has a +1 charge. And if you look at up and down, you can probably figure out if there are going to be 3 quarks total, how does it need to be situated so that the up quarks and the down quarks leave you with a +1 charge? Well, one of the quarks is an up quark. That gives me 2/3. If I have another up quark, that gives me 4/3. And then a down quark brings that down to 3/3, which is a +1 charge. So we have an up, up, down. Sometimes we can draw it like this as a group of 3 quarks, or sometimes you might see it just represented in parentheses. UUD, up, up, down, is the quark combination for a proton. For a neutron, we know that that is a neutral charge. So likewise, you can probably figure out the combination of up and down quarks to make that neutral happen. Well, here we have a down quark, and an up quark. So 2/3 and then minus 1/3 brings us down to 0 for our neutral neutron. That is a UDD, or up, down, down configuration. So again, these are both baryons because they're made out of 3 quarks. Let's look at some mesons. These mesons are always going to be formed with a combination of quark and an anti-quark because the rule always stays the same here that you must have an integer value, -1, 0, or +1. So if I look at this kaon here, I've got a down quark, and again, this bar on top means it's an anti-strange quark. Well, find on my list down quark is a negative 1/3 charge. Then I find strange is here. Well, strange says it's a negative 1/3, but since it's an anti-strange, that becomes a positive 1/3. So I have a negative 1/3, positive 1/3. They cancel each other out, and we have a charge of 0. Now we can do the same thing for a D meson. A D meson is a down quark and an anti-up quark. So we can figure out what that charge needs to be. The down quark, again, here, is a negative 1/3. An up quark is a 2/3, but it's an anti-up quark, which makes it a negative 2/3. So my D meson, I can predict will have a charge of -1. And we can do this with any meson or baryon that's given to us because we can use this table to help us identify what the charge of the individual parts are going to be, which can help us figure out the charge of the whole. All right, so we've seen these two quark combos or these three quark combinations. Well, what about one quark combinations? Well, it turns out that quarks have never been observed on their own. This is a phenomenon known as quark confinement. And you might think, okay, well, let's take a meson, which only has two, and let's rip those quarks apart. Let's add energy so that the quarks are no longer together. Well, turns out that the amount of energy required to overcome that strong nuclear force that's holding those together is actually enough energy to be converted into mass and create two new quarks along the way. So if you were to add enough energy to separate the quarks, well, too bad, because that energy was converted into mass and you have two mesons now instead of one. So quark confinement means that quarks will never be found or observed on their own. And then another thing that we'll need to be able to talk about in these particle interactions will be conservation. We're familiar with conservation in chemistry, conservation of mass. You might be familiar with our conservation is conservation of momentum or conservation of energy. We've talked about that in physics as well. But here, there are some different properties that are always conserved in the world of particle physics. And the properties are baryon number, lepton number, charge, and strangeness. Strangeness will really only ever apply if there are strange quarks in here. So we're not going to see strangeness here in these slides, but you might encounter them later on. Let's focus primarily here on baryon number, lepton number, and charge. Well, if I see my particle interaction presented as is here, I have a neutron, which turns into a proton, an electron, and an antineutrino. That might feel familiar. That is the process that kind of underlies the beta negative decay that we talked about earlier on in the unit. Well, if I look at my list of quarks, I see that baryon number shows up in that list. And every quark has a baryon number of 1/3, and an anti-quark would just have a negative 1/3 baryon number. Well, here I know that a neutron is made out of three quarks, so 3 times 1/3 will give me a baryon number of 1. Any baryon number will have a baryon number, or any baryon has a baryon number of 1. A neutron is. A proton here, same thing, three quarks, gives me a baryon number of 1. An electron and an antineutrino are not quarks. They're not made out of quarks. They do not have a baryon number at all. So they are both 0 for their baryon number. Baryon number is conserved. I have 1 on both sides of that particle interaction. Next, let's look at a lepton number. To find that, I need to look at the lepton table on my data booklet. Here, all leptons have a lepton number of 1, and antileptons have a lepton number of -1. Nothing said there about anything made out of quarks. Neutrons and protons both have a lepton number of 0 because there are no leptons associated. So an electron here is a lepton that has a lepton number of 1, and this antineutrino is an antilepton, which means it has a lepton number of -1. Lepton number is conserved. I have 0 on the left-hand side, and then 0 plus 1 minus 1, which gives me 0 as well. All right, my last piece here is the charge. Charge, we know for neutron is neutral. That's 0. For a proton, we know that's +1. For an electron, we know that's a -1. And then here, you can look at these other leptons. This antineutrino, doesn't matter if it's a neutrino or antineutrino, it will have a charge of 0. Again, charge is conserved, just like these other numbers were. 0 turns into 1, -1, plus 0. So this interaction is valid because all of these properties are conserved. Now let's look at a couple more examples. If I give you two more situations here, you can look at each of these numbers and see if these numbers are conserved. You may not recognize the configuration of the things that are shown, but looking at conservation, even if you're not familiar with it, you can determine, is this valid or is this not valid? Is this something that could happen or not? So again, here are the three different properties, ignoring strangeness number for now, that we're going to keep trying to conserve. So if we look at the left side of this interaction, proton has a baryon number of 1, a lepton number of 0, and a charge of +1. This electron has a baryon number of 0, a lepton number of 1, and a charge of -1. All right. Now the right-hand side, my neutron is a baryon number of 1, lepton number of 0, because it is not a lepton, and a charge of 0, because it is neutral. And then my neutrino is a baryon number of 0, because there are no quarks, a lepton number of 1, because it's not an antineutrino like we saw before, and then a charge of 0. Everything seems to be conserved. Baryon number is 1 on both sides, lepton number is 1 on both sides, and the charge neutralizes to 0 on both sides. So yes, that is a valid particle interaction. Now, if I look at this one down below, I've got a neutron and proton. Those are both baryons, and not leptons. So baryon number 1 and 1. Lepton number is 0 and 0. And then the charge is neutral for the neutron and +1 for the proton. All right, I'm going to look over on the right-hand side. I've got a positron, which is an anti-electron, and an antineutrino. That means that their baryon number is 0 for both of them. There's no quarks. Their lepton number is -1 because they are both anti-leptons. Even though we don't see the bar over the top of this positron, it is an anti-electron. It's just another way of writing that. And that means we have a charge of +1 and a charge of 0. Looks like charge is conserved, but baryon number is not. We have 2 and 0, and lepton number is not, 0 and -2. So this is invalid. These particles cannot interact in this way, because these properties are not being conserved. All right, the final type of particle that shows up in our standard model that we'll be seeing is something called an exchange particle. Exchange particles are ways that we can explain force in terms of particles. So the particle model, the standard model, means that everything is made out of particles or can be explained in the form of particles. Well, force is one of those weird things to try to explain as a particle. If two things are being repelled, how is a particle doing that? Well, there are a couple different conceptual models that can help us understand that. One is imagine that we have this particle, this bowling ball, giving us this force of repulsion. And imagine that that bowling ball is just making the rounds going back and forth. When it leaves one particle, it kind of sends it out. When it's caught by another particle, it sends it backward. And if that bowling ball keeps going back and forth, you can imagine these two skateboarders drifting apart farther and farther, that force of repulsion. Um, Now, here to get a force of attraction is a little bit harder. It's kind of a stretch, but imagine instead of a bowling ball, we have a boomerang. So it's being thrown opposite, kind of going back and around and being caught opposite. And each time it's thrown and caught, those skateboarders get a little bit closer together in this form of attraction. Well, these interactions, they're not observable. We don't see these particles going back and forth. We call these virtual particles. It's a way of describing forces. Everything can be described in this form of particle nature. All right, these four forces that we've seen before, gravitational, weak, electromagnetic, and strong force, are the four fundamental forces. You'll see that each of these have mediating particles. The gravitational force, we call the mediating particle a graviton. The weak force has a few different particles that we'll see in the next lesson, the W plus, W minus, and then Z naught. Electromagnetic has this gamma that is our symbol for a photon, and then strong nuclear force is gluons, sticking the protons and neutrons in any baryon or hadron together. Now, these are arranged in the data booklet in order of weakest to strongest. Strong is our strongest, go figure. And gravitational is actually by far the weakest force, which is weird because that's the force that seem to experience in our own lives the most. But it is by far the weakest. It's weak enough that you can actually overcome it by simply jumping. You are not going to be able to overcome something like the strong nuclear force by any force that you are able to impart. And every once in a while, IB will ask a question kind of surrounding these ideas. Which of the following lists three fundamental forces in increasing order of strength? Well, if you know that the data booklet gives it to you in this increasing order, you can pretty clearly find the answer. In this case, there's only three different examples that are shown, but gravity, weak nuclear, and electromagnetic are in the correct order, left to right. All right. That leads us to trying to summarize and understand all of these things together. And we do so in something called the standard model.
The objective of particle physics is to understand the basic structure and laws in nature. All the way from the largest dimension in the universe, formation of galaxies and stars, all the way down to the smallest dimension in the microcosm.
So historically, we knew about all of the different elements in nature. We knew about helium, hydrogen, oxygen, gold, lead, and so on, which are all made of different atoms. But a great simplification was made when we realized that all the atoms are just made out of three particles, the protons, the neutrons, and the electrons. And just by adding more protons, more electrons, we get a different element, different type of atom.
In principle, you can build a very simple universe with just protons, neutrons, and electrons.
But it became much more complicated in the beginning of the 20th century when we found many, many new particles from cosmic rays.
There wasn't really a system established to organize this zoo of particles.
So we were calling these new particles things like pi, sigma, delta, and so on. And things got so bad we were running out of symbols to name these particles. So we started organizing these particles according to the properties they have. And the properties are things like spin, electrical charge, so if they're positively charged, negatively charged, or neutral, mass of the particles, and the lifetime of the particles, which is how long it takes before they decay into lighter particles.
To simplify the picture, new fundamental particles called quarks were predicted. And the whole zoo of particles could be described by combinations of these quarks. And this was the birth of the standard model. At the beginning, there were only three quarks. Then a fourth, fifth, and sixth quarks was predicted and then discovered, and this gave us great confidence in the model. In addition to these quarks, there's another set of fundamental building blocks of matter, the so-called leptons. They are composed of an electron, their heavier cousins, the muon and the tau, and their neutrino partners. In addition to the fundamental building blocks of matter, the standard model also incorporates the fundamental forces. The exchange particles of the weak force are the W and the Z boson. The weak force explains the energy production in the sun and is responsible for the radioactive beta decay. The electromagnetic force acts on charged particles. The corresponding force carrier is the photon. The electromagnetic force is responsible for propagation of light or for the fact that a magnet can pick up a paperclip. The strong interaction acts on the quarks. The corresponding force carrier is the gluon. The gluon literally glues together the quarks in the neutrons and the protons, and it holds the nucleus together.
The standard model is extremely successful, and it has predicted all the phenomena we have seen so far at the microscopic level.
This is a beautiful theory. It is self-consistent, it's predictive, but it's incomplete. There's one last missing piece of this puzzle, and that's the Higgs boson. It's the holy grail of particle physics.
We know exactly what it should look like, and we have predicted this particle since over 40 years, and we use it in all our calculations and so on. We're pretty sure it's there, but we haven't found it so far.
All right, that's where we'll stop that video, because in the next lesson we will talk about the Higgs boson, because since the creation of this YouTube video, it has been discovered and measured in the Large Hadron Collider.
And now
So, um, a sample IB question just to understand kind of the creation of this standard model. For what reason were quarks first introduced? Well, one of the things that they described very well in that video was basically is trying to find patterns, just like Mendeleev and other scientists around the time of the periodic table used that to better understand these other patterns that were happening and predict things that they had not found yet. Here, quarks were first introduced just to create some patterns in these hundreds of particles that were being discovered. Just like how the 118 different elements can all be described in just simple combinations of protons, neutrons, and electrons, these hundreds of different hadrons, baryons, and mesons can be described as just different combinations of these 12 different quarks that there are. So all of that leads us to the standard model, and we'll be focusing more on this in the next lesson as well. But all of these different particles can be arranged in a periodic table-like arrangement. So here you'll see on the left-hand side, these are the most common different particles that we'll be seeing. Up quarks, down quarks, electron, neutrino, and electron. These are the ones that make up these chemistry particles that you're familiar with, like protons, neutrons, and electrons. You'll also notice that there's one other particle here that wasn't presented in the video, the graviton. It was in the data booklet talking about the force carrying particle for gravity, but it is still currently undiscovered. This has not been measured. Gravity is kind of a mystery still in terms of particles and really how it even works. So we'll talk a little bit more about that as well. All right, from this video, you should be familiar with these different particles, these different quarks and leptons, and now how they can be combined or transferred in these different particle interactions using the conservation of charge, baryon number, and lepton number.